Okay. So, in the previous class, I gave a small problem for you to work out. So, I am not sure whether you have done it or not, but I would like to spend some time now to solve that problem for your sake. Okay. Let me quickly repeat the problem that I gave. We said that there is a box, there are 4 boxes. Box 1, it consists of 2000 items, out of which 1900 items were good and 100 were defective. Box 2, it had 300 good items, 200 defective items. Box 3, it had 900 good items, 100 defective items, and last box, box 4, it also had 900 good items and 100 defective items. Question that was asked was that, we select any box, any particular box at random first, and then from that box we remove just only one element. Then the first question is, what is the probability that the particular element which is being removed is a defective one? Okay. So, to answer that, first we see that each of the boxes, since the boxes they are chosen purely at random and there is no particular preference for a special box, maybe box 1, box 2, box 3 or box 4, the probability that I choose box 1, say B 1 or B 2 or B 3 or B 4, that is 1 by 4, because it is uniform. That means, P B 1 is same as P B 2 is same as P B 3 is same as P B 4 is equal to 1 by 4, they are uniform. This is a very safe assumption, because there is no preference for a particular box. Okay. And then right across I can write that suppose I choose box 1, then what is the probability that the particular item that is removed from that box is a defective one. Okay, that is P D by B 1. This is equal to, now there are 2000 elements, out of which only 100 are defective, right. So, probability that the particular particular item which has been removed is defective is having a probability 100 by the total, that is 2000, okay, which means 0.05. Similarly, P D by B 2, that is assuming that box 2 has been selected, condition to the fact that B 2 has been selected, what is the probability that the element that is removed, item that is removed is a defective one. So, in this case total number of items is 500 and 200 are the defective ones. So, probability is 200 by 500, that is 0.4. Okay. In the same manner, P D by B 4, sorry, this is B 3, just a minute please. Now, here total is, in total we have 1000 elements and 100 are defective. So, this will be just 100 by 1000, which is 0.1, and this is identical to this. So, P d by B 4, this is again 0.1. So, the question is, what is the probability that the item that is removed is defective? So, we will apply this total probability theorem. There is probability that the selected item is defective is given by that is assuming B 1 is selected, the probability is P B 1, then condition to that the probability that is defective is P of d by B 1 plus P d by B 2 and we now know all these values. These are all 1 by 4. So, you can take 1 by 4 common and these individual probabilities are 0.01 plus I think 0.4 plus 0.1 plus 0.1. Okay. That makes it in fact, if you calculate it will turn out to be. So, this is the probability that the selected item is a defective one. Okay. That is the question that I had asked of you in this in my previous lecture. But now I append another question to this, that is, suppose the item selected has been found to be a defective one, then what is the probability that this item has indeed been picked up from say particular box, say box 1, what is the probability? For that we will be using this Bayes rule. We know that so, you consider box 2. What is the probability that the ball has been removed from box 2? So, this we know 0.4. Question is, what is the probability that, I mean, given that the ball that the item that has been removed is a defective one, subject to that, now what is the probability that the item has been picked up from box number 2? That is this probability. That is equal to what? That is equal to by what we studied earlier, first if you take the multiplication, this is the joint probability. If you take this P d by B 2 into P B 2, there is a joint probability that box B 2 was selected and the item removed from it was defective. But the joint probability is nothing but P B 2 by D into P D, okay, or this is equal to nothing, this side divided by P D. In fact, we have established this relation in our previous class. So, I am not speaking much on this, but roughly you can remember it like this. That is, if you take the product of the two, again you get a joint probability between B 2 and D, because this is B 2 by D, probability B 2 by D, and this is probability of D. It is the other way here, probability D by B 2 into probability B 2. Both cases we get joint probability of D and B 2. Okay. And now these figures we know, because P D has been evaluated. These were given that the box was B 2, the probability of this being defective was 0.4, probability of B 2 is 1 by 4 as we know. So, this is 0.4 into 1 by 4 divided by P D, which is 0.1625. I think this turns out to be 0.615. all right. So, this is the answer. Okay. So, towards the end of our previous class, we had just introduced you to the concept of statistical independence of events. Okay, statistical independence of events. I now try to highlight that and also discuss the various properties that are associated with this notion, and I will try to give an example also to explain it further. Suppose we consider two events A and B, both belonging to the certain event S, there is a total set S. Okay. In terms of Venn diagram, you can have something like this A, this is B, this is the overlap area, there is A B, all these we have studied earlier. Okay. Now, question is, if A and B, the events are such, then if I look for the probability corresponding to their intersection, which means they are joint occurrence, because it is here we have both A and B occurring simultaneously, both are present, that is joint occurrence, that is P A B. If this is nothing but just the product of P A and P B, P A is the probability of event A, P B is the probability of event B, then A and B will be called statistically independent. Okay. I am trying to give you the physical meaning of this, but before that you can see one thing, you can always write P A B, this is always true, that P A by B into P B, this is always true irrespective of whether these two are statistically independent or not. This we have already established. This comes from the definition of the conditional probability in fact. Now, if they are statistically independent, then P A B is also given by this, and since P B is non-zero, okay, suppose we do not count the case of P B being 0, then obviously P A by B is P A. In fact, how did we discard this possibility of P B being 0, because we are not considering any event which is an empty set, that is which is an impossible event. Only for impossible event the corresponding probability is 0, that I am not considering, which means P B is a non-zero positive number less than 1, okay, positive real number, and which means P A by B is same as P A. That means actually that even if we first ensure that B has taken place and subject to that try to evaluate the probability of A, the probability should be the actual probability of A irrespective of the fact that B has already occurred. This is the meaning, and this can happen if B and A are two such physical events which have no connection between them. Then whether B has occurred or not, if you try to evaluate the probability of A, you will always get P A. So, P A by B is P A. That is the meaning of the statistical independence of A and B, which by definition is written like this. Okay. We can just look into the corresponding frequency interpretation also. Suppose we are conducting experiments and on n occasions, total number of trials is n, small n, on n occasions A occurs, sorry, A B occur. So, number of occasions. Okay. In that case, what is PAB? That is simply NAB by N. Let me put an approximate sign, because after all this is not the exact probability, but this is just the frequency interpretation. So, NAB by N, and now we know what is PA, that is NA by N, what is PB, that is NB by N. And if these are statistically independent, then it would mean this PAB, we can always write it like this, N B, then N B by N, we can always write like this. Okay. And what is N B by N? That is P B. Okay. And what is this? P A by B. Okay. But this turns out to be N A by N. Okay. That means the fact that on N B occasions B has occurred has got no impact on the probability of A's occurrence. Okay. It is just repetition of what I stated using symbols earlier. So, whether B has occurred or not, that is N A B by N B, provided all these number of trials are large, N B is large, N A B by N B will turn out to be what we get as N A by N only, provided B has got no connection with A, that is B and A are physically and statistically independent of that. Okay. This is P B, okay, and this is P A by B, but by definition P A B, if they are statistically independent, is equal to P A into P B, which means this is P A, and if this is P A, that means N A by N ratio will turn out to be same as this. That is, if I just take n number of trials and find out total number of times N A has occurred and take this ratio, whatever I will get the same thing if I take N B number of trials, that is trials where first it is ensured that B has taken place, then find out how many times A has taken place and take the ratio, I will still get the same value as I get here, provided of course these are large enough. That means the fact that B has occurred has got really no impact. I mean, whether B has occurred or not, I get the same probability of A. Then only I say that B and A are statistically independent. Okay. Then certain properties follow from this. Given that okay, that is giving that the two events A and B are statistically independent, we should have P A bar B is also written similarly, that is the two events A bar, that is A complement and B, they are also statistically independent. Further, P A bar B bar, these two also are statistically independent. Okay. It is not difficult to show this. First consider this. We know that any event B can be written as a union of two mutually exclusive sets. One is A B, another is A bar B. If you have forgotten, I just draw a Venn diagram here quickly. this is A, this is B. So, this is the diagram. Okay. This part is A B, this part is A B, and this remaining portion of B is nothing but intersection between A complement, that is the area outside A, and B. There only this portion will be absorbed, right, and these two portions are mutually exclusive. So, B can be written like this, we have seen it already earlier. Okay. But since they are mutually exclusive, P B is nothing but okay. And you have given me the fact that A and B are statistically independent, which means I can write like this. All right. So, I take this P B to the left hand side. Take that as common. So, you get now what is 1 minus P A? This is nothing but P of A bar, because you remember P of A and P of A bar, the two probabilities when added their value is 1, because A and A bar when put under union they correspond to the total set, that is a certain event. So, its probability is 1, which means P B, which means P of A bar B is same as P A bar into P B. All right. This implies A bar and B are statistically okay. This logic you can now apply again. It is given, suppose that A bar and B they are statistically independent, which means A bar and B complement, that is B bar, they are also statistically independent by the same argument. A bar is one event, earlier it was A and B and then complement came over A, B was left as it is, and now you are given this fact that A bar and B are statistically independent, then keep A bar as it is, complement B. So, you get A bar and B bar. By the same development again I can say that A bar and B bar also are statistically independent, just repetition of the same argument, which means okay. Just to give an example, Gaussian experiment where we are tossing a coin just twice in succession. So, when the head comes I say the outcome is H, when tail comes it is T. So, there are 4 possibilities, is not it? S consists of here H H, that is head first, head second, H T, that is head first, T second, then T H and T T. Okay. Now, suppose you select two numbers A and B, A B, greater than 0 and A plus B 1, so that they qualify for some probability actually. Okay. The real numbers, it is given like this. Suppose we select any such pair A B, and then it is giving us beforehand that P of H H is nothing but A square, P of H T is same as P of T H, that is equal to A B, okay, and P of T T is B square. Then there is no conflict, because what is the total event, either H H or H T or T H or T T. So, probability of the total event is what? This plus this plus this plus this, A square plus A B plus B square, which is A plus B whole square, and A plus B being given 1, that is 1. So, that is satisfied, and each probability is having value greater than 0 and less than 1, there is no problem. Suppose this is given to us. Then we consider two events. In one event, head first, that is I consider those subsets, these are outcomes mind you. This certain event has these possible outcomes, head head, head tail, tail head, tail tail, and then I can construct events by taking their forming the subsets. Suppose I now consider those cases where head is first. So, I consider those subsets, that subset where H comes first. Okay. So, event 1 head first, okay, meaning H H H T. What is the probability of event 1? Probability, I can call it say P H 1, H 1 stands for say event 1, that will be what? Since they are mutually exclusive, I mean these two, and the probability of this total event will be what? See, either this can happen or this can happen, they cannot happen together, they are exclusive. So, what is the total probability? Total probability will be the probability sum of the probability for this and this, which means A square plus A B. Okay. Take A common, A into within bracket A plus B, and A plus B is 1, which means this is equal to A. All right. So, head first, its probability is A. Okay. Similarly, we now consider second event, that is event 2 head second, meaning T H or again H H, head second. So, here probability of this event is P H 2, again A B plus A square, take A common and you get A, because A plus B is 1. All right. Question is, are these two events statistically independent? From a physical sense, yes, because whether head first or head second, these events they really physically have got no influence on each other, isn't it? But mathematically, does it satisfy the axiom for statistical independence, that we can verify? So, just to check whether H 1 and H 2 are statistically independent or not, what do? We take the probability of the joint event H 1 H 2. Now, what is a joint event? H1 had HH and HT, and H2 has TH and HH. So, they can jointly occur only in the form of HH. If both have to occur jointly, okay, then only HH can take place. Okay. So, that means this will be nothing but the probability for HH. Which is equal to A square. But what is PH1, PH2? That is again A square. We have found out that in both cases the probability is A, which means these two events are statistically independent. Okay. So far for statistical independence. Okay. So, I conclude this particular section and I will go to the following topic now, but then I think it is proper that we sum up as to what we did, what we have done so far. We started in our first lecture with a description of the course. We tried to develop the need for a formal treatment to probability, which we did by forming some probability axioms. So, towards that we first started with the concepts of set theory, because the theory of probability has been built around set theory, okay, on a set of events. Then we established, we proposed or stated rather certain axioms of probability, basic axioms. Only a few axioms need to be satisfied by the probability, and then we discussed the corollaries that come from those axioms. Okay. We took up some examples then we moved over to something called conditional probability. Then we discussed total probability, probability or Bayes theorem, okay. And then we took up some examples to explain that, and then we came to this notion of statistical independence. Okay. And the statistical independence is a very useful concept and very widely used concept, okay, which we will study later, which we will see later as this course develops. So, this is for this general definition of probability. Okay. Now, I move to the concept of random variable. All right, even though we say it is variable, actually random variable is more a function than a variable. But only problem is in our day to day business, we tend to lose sight of its role as a function, and we try to take it as a variable. So, to give let me formally write before that, let us consider this idea of a function. What is a function? Function can be continuous or discrete, but always any function, it takes basically some member of a particular set and maps it to another member of a set. The source set on which it works, it is called the domain, and the set which where it maps actually the domain, it is called the range, right. For instance, we often write a function like this x of t. Now, here t could be, t corresponds to a particular set, is a member of a particular set. It so happens that often this t is a member of a set of continuous, t is a continuous valued parameter, means that t is a member of a set of continuous valued real numbers actually, okay, there is a real line. Then for each element on the real line, for each t, this x t gives us another real number. So, that sort of a mapping, but it could have been a discrete, it could be a discrete parameter, that is t can come from a set, maybe finite, maybe infinite, of some discrete elements. X of t is nothing but a function which works on those elements and gives you some value. Value could be complex or real valued or any other I mean, if not real, complex, it could be binary also. Okay. It can belong to any field. That is the general notion of function. Now, suppose in the context of our probability, I say things like this, that suppose we are considering an experiment. Okay. So, experiment has got various outcomes. You consider the set of all possible outcomes, that is the certain event S. Now, what I do with each outcome, I assign some particular value. I say that if this outcome has taken place, let the value be this much, or if that outcome has taken place, let the value be that much, but the values are fixed once for all. That means, if you go on conducting the experiment, you keep getting new and new experimental outcomes. Of course, all experimental outcomes belong to that total set S, but each time you look at the value, you see that the value that is taking place is random. So, if you have a value chart, you will see various values are coming. Again, values are pre-assigned, it is not that they are taking arbitrary values, because you already have a set of pre-assigned values, and whatever value you are now getting, they correspond to that set only, but you are getting this a chart giving this random occurrence of these values. Here we say, I mean, this process of assigning value to each experiment, you can again view it in the same way as we have the notion of functions. That is, we can say that let x it maps the set S to a set of numbers. For making our life simple, we are considering real values, but it could be complex. So, S is mapped to R. Physically, it means x is a function which works on each element of S, means each experimental outcome of S. For each of these experimental outcomes, this function picks up a value from R. R is the set of all real numbers. Okay. That means, what is the domain here? That is, A is a particular experimental outcome. So, I am considering all experimental outcomes belonging to S. For each outcome, x of A is the function which picks up the particular outcome and gives you a value from R, and the set of all values, okay, that forms the domain. So, x just picks up those outcomes and maps a particular outcome to a particular value in the domain. So, this x of A, ideally this is called a random variable. So, actually it is a function. Okay. Actually it is a function. Okay. So, x of A, it means basically a function, as I said, but often what happens, we take x as some kind of variable, in the sense that x equal to what? X equal to, for this we are measuring, we are doing some experiment, we are measuring something, what is the x? Next time what is the x, and like that. So, x is treated most often in practice as some kind of a variable, because we directly look into the value of x. Actually, that is, from our point of view, from our consideration, this fact that there is an experimental outcome on which x is working and giving you the particular value, that aspect is hidden. For instance, suppose there is a furnace, every 5 minutes you are measuring temperature of a particular section, Okay, there are various possible temperatures, okay, maybe a continuous range of temperatures, maybe certain discrete upper approximations and discrete range. Okay, they form a set of experiments. When you measure using a thermometer, the value that you are getting, that actually is a function, that is the this temperature. I mean, it just takes one of those events, and this measurement, rather measurement of temperature, it takes one of the states. Suppose the furnace has certain states, as a state 1 or state 2 or state 3 or state 4, each state is characterized by a particular temperature, and these states form the events. The process of measuring the temperature actually by a thermometer or whatever, what it does, it picks up one of those states, that is one of the events, and then gives you a particular value. That value is a temperature, say T. Unfortunately, in practice we will be taking T only, we will be taking T as some kind of a variable. Okay, then we measure temperature. Now, what is T? Okay, T is so much degree centigrade. Next time, what is T? Okay, T is this much, and like that. So, for us T will appear to be some kind of variable, but actually, and we loosely call them random variable, but actually along with each random variable there is this interpretation of an experiment that goes on, and the random variable is nothing but a mapping of particular event to a particular experimental outcome, rather not even experimental outcome, to a real number. I am pursuing real valued random variables, so a particular real number. Okay. Then just to give an example, suppose you are like I give an example of the furnace, but let me give another example to make this point clear. Suppose I take that tossing a die experiment. A die has got 6 faces. Let the faces be F1, face 1, F2, F3, F4, F5, F6. F1 means the top face is marked with 1, F2 means the top face marked with 2, and likewise. At each of the states, each of these faces has probability 1 by 6, because it is an unbiased die. All right. What do we do? We conduct an experiment. One of the faces show up, and based on what we have, suppose we generate a particular value, and we generate by some mechanism. In this case, the mechanism is, that is, let me write it out. Okay. We have got 6 faces, F I from 1 to 6. Okay. So, any of the F I will be, each F I is a particular experimental outcome. So, there are 6 outcomes, and total set is nothing but a set consisting of F1, F2, F3 up to F6. What do we do? The moment a particular event takes place, particular outcomes takes place, the F I, we assign, we find out this variable x is equal to as 10 I, which means when F1 takes place, that particular value, that will be 10. If F2 takes place, it will be 20, then 30, 40, 50, 60. So, every time you conduct this experiment, you get one particular value from that state, 10, 20, 30, 40, 50, 60. Okay. So, in this case your function, it maps each outcome. Okay, there is a function which maps each of the outcome to a particular number, F1 to 10, F2 to 20, and like that. That function actually is described like this. Actually, I should have written x as a function of I, because I is the event. But as I told you, often we really do not, we just deal with this particular variable, and often that mechanism of experiment and particular experimental outcomes and all that, that remains hidden from us. That is why we most often treat the variable as x itself rather than calling it at x of some event, x of some experimental outcome I. All right. Then comes this issue. One particular notation, certain notations are important here. Now, what does it mean? We know x is a random variable. The x, now what is x actually? That we know that there is a set S, it consists of all experimental outcomes, set of outcomes A, okay, A's. Now, with each outcome, as I told you, we associate, we have a function actually, x should be strictly a function of this outcome, that is on each outcome there is a function which works and gives you a number. So, actually it is dot x, it should be x of A, but loosely as I told you earlier, we omit this dependence on A, we simply say x. In any case, x then stands for a number which is associated with a particular outcome. Okay. For each outcome, the corresponding x gives you one particular number, and since these outcomes are occurring randomly, that every time you perform an experiment you get some outcome or other, the value that x takes, okay, is also random, because you at every trial or at every experiment you get some new value or different value. So, that values occur also, numerical values also occur randomly, that is why it is called random variable. Now, coming to this, what does it mean? Capital X is a given number, and when I say x less than or equal to capital X and I put parenthesis, what does it mean? Now, this notation we have to first make clear, but before that let us tell you this, that in probability theory we often try to ask this question, that okay, given a number capital X, what is the probability that small x, the random variable, is less than or equal to capital X? Now, as you know, we have defined probability not on numbers, not on x or capital X, but we have defined probability over events. There is a set of all possible outcomes, then subsets of that set they form the events. With each event we have a probability, and we have given the axiomatic definition of probability already. So, events probability is always associated with the events, not with the numbers. But in probability theory or random variable theory, since we talk in terms of random variable where x is actually a function, but we don't show that functional form, but just write x, but actually it means that there is some experimental outcome upon which and based on that outcome x takes some value, and in that sense x is random. Okay. So, in that background, question is what is the meaning of this, or rather if I want to say that what is the probability that random variable x is less than or equal to capital X, how to define it? You understand my point? My point is, so far probability, the notion of probability has been defined on set, that is events, not on numbers. So, that means if we have a situation like this, a condition that given to us like this, that x is a random variable, but it takes values less than or equal to a given number capital X. This situation somehow we have to convert into the language of equivalently into these events, that is we have to somehow find an interpretation of this situation in terms of the events, that is sets or subsets, then we can talk in terms of probability. Okay, because probability is not defined on these numbers, it is not defined on a variable x so far, okay, it is defined only on sets. So, we define, so when we write this x less than or equal to capital X, we actually mean an event, and when I say probability of small x less than or equal to capital X, it actually means probability of that particular event which is associated with this. Okay. Now, what is that event? That event means, as you know,
the set consists of several outcomes. With each outcome, I have got a value for random variable x. Now, from all those outcomes, now isolate only those for which the value that x takes is either equal to x, capital X, or less than capital X, okay, and collect them. So, if that forms a subset of capital S, which means it is an event, okay, because it is a subset consisting of some outcomes. So, that means this is nothing but a subset of S having outcomes A or A's, so that x of A, actually as I told you, random variable x is actually a function, it takes the outcome and gives you a value. So, x of A is less than or equal to capital X. So, I find out those outcomes only for which x takes values less than or equal to capital X. Set of those outcomes definitely is a subset of S and definitely is an event that has a probability. So, probability of small x less than or equal to capital X equivalently means probability of that event. Which event? That consists of those outcomes for which x takes values less than or equal to capital X. Okay. Then sometimes we ask this question, given two numbers x 1 and x 2, what is the probability of this? What is the probability, P for probability, what is the probability of x lying within this, less than or equal to x 2, greater than or equal to x 1? Again, this statement is nothing, x less than or equal to x 2, greater than or equal to x 1. Okay. It is purely in terms of number and variable, two numbers x 1, x 2 and x is a random variable. That as such, I mean I cannot apply probability on that, but I have to convert this condition into a condition involving events. I have to convert this condition into some event, and on that event definitely we have got the notion of probability working. Now, this will imply this is same as the probability of that event. Just a minute. This is equivalent to probability of this event. What is this event? I will tell now. When I put curly bracket, this becomes an event. Now, this is what is this event? This actually denotes an event. What is that event? It is set of, rather I would say subset with outcomes is so that the random variable is less than equal to, it takes the value that is less than equal to x 2, greater than equal to x 1. That is, from the given set S, okay, you isolate, you find out only those outcomes for which x takes values within this range x 1 to x 2, because with each outcome I have got some value associated as expressed by x, which is actually a function of this outcome. So, I am just again collecting some outcomes for which all those outcomes, mind you, I am not leaving any, I am collecting all those outcomes or all those elements of the set S, so that for each element, that is for each outcome, if you for each of those outcomes, if you take the value of the random variable, you get a value within the range x 1 to x 2. But that is again a set of some outcomes, okay, that is set of, that is a subset of A, which is an event, and on an event we have a definition of probability working. So, probability of x lying within this range capital X 2 and x 1 is same as probability of this event, that is, I mean probability of this event occurring, that is, I mean probability of occurring, probability that some outcome occurs, so that x of that outcome, that is a random variable, takes values within x 1 to x 2. Okay, that is the probability of that event. Okay. Similarly, if I say probability of say x equal to a, some number a, it means it is equivalent to probability of this event, again curly bracket stands for event here, x equal to a, where this event means x equal to a is a condition, but when I put within curly bracket it means an event. Event means some subset of S, it gives rise to a subset of S, or it indicates a subset of S. What subset? That is such a subset of S with outcomes S so that x a is equal to a. Okay. Finally, formally we define the random variable like this. X is a random variable RV, RV stands for random variable, if number 1 this event, this is an event for any, important is any given x, means you give me any number x and then you find out x less than equal to x within curly bracket, means you try to look for some outcomes of S or those outcomes of S, okay, for which the random variable takes value less than equal to capital X, okay, less than equal to capital X. Clearly, that is this should be an event, that is we should really be able to find out such outcomes. So, this must be an event. Okay. And number 2 is the two things, probability of x taking value infinity and probability that should be equal to probability of taking x value minus infinity, both should be equal to 0. Okay. That is a formal definition of a random variable. Okay, that is all for today. Thank you.